students, let's begin with a simple thought. Have you ever noticed how some salts, like table salt, dissolve almost completely in water, while others, like barium sulfate, hardly dissolve at all? This brings us to an exciting concept, solubility equilibria of sparingly soluble salts. The solubility of ionic salts depends on two competing forces, the lattice enthalpy that holds the ions together in the solid and the solvation enthalpy that helps break them apart and surround them in water. If solvation energy wins, the salt dissolves well. If lattice energy dominates, the salt remains sparingly soluble. Based on this, salts are broadly classified as soluble, slightly soluble, or sparingly soluble.
To describe this behavior quantitatively, we use the concept of the solubility product constant, or KSP. Let's take the example of barium sulfate. At equilibrium, solid barium sulfate, when in contact with water, dissociates into barium ions and sulfate ions in solution. The equilibrium constant is expressed as K equals the concentration of barium ions multiplied by the concentration of sulfate ions. Since the concentration of the pure solid barium sulfate remains constant, it is excluded from the expression. This K value is what we call the solubility product, or KSP. Remember, the solubility product is fixed at a given temperature and is independent of how much solid is present in contact with water. Now let's link the solubility product, KSP, to solubility. The molar solubility, denoted by S, tells us how many moles of a salt dissolve in 1 liter of solution. For barium sulfate, if the solubility is S, then the concentration of barium ions is S, and the concentration of sulfate ions is also S. Substituting into the expression for the solubility product, we get KSP equals S squared. For example, if the solubility product of barium sulfate is 1.1 times 10 to the power of minus 10 at 298 Kelvin, then the solubility S equals the square root of 1.1 times 10 to the power of minus 10, which comes out to about 1.05 times 10 to the power of minus 5 molar. This simple relation shows how the measurable solubility of a salt connects directly to its KSP value. But not all salts are as simple as barium sulfate. Some salts dissociate into more than one type of ion. For a general salt written as M sub Px sub Q, it dissociates into P positively charged ions called cations and Q negatively charged ions called anions. The solubility product expression then becomes KSP equals the concentration of the cation raised to the power P, multiplied by the concentration of the anion raised to the power Q. If the molar solubility is represented by S, then the concentration of the cation is P times S and the concentration of the anion is Q times S. Substituting these values, we get KSP equals open bracket, P times S close bracket raised to the power P multiplied by open bracket Q times S close bracket raised to the power Q. This general formula allows us to calculate the solubility for any salt, no matter what its stoichiometry is. Let's solve an advanced example. Suppose we have a salt represented as A2X3, with a solubility product KSP equal to 1.1 times 10 to the power of minus 23. The dissociation is A2X3 breaks apart to give 2 A3 plus ions and 3 X2 minus ions. If the molar solubility is denoted by S, then the concentration of A3 plus ions equals 2 times S, and the concentration of X2 minus ions equals 3 times S. Substituting into the solubility product expression, we get KSP equals open bracket 2 S close bracket squared multiplied by open bracket 3S close bracket cubed. That simplifies to 108S to the power of 5. So we have 1.1 times 10 to the power of minus 23 equals 108 times S to the power of 5. Solving this, S equals 1 times 10 to the power of minus 5 molar. This step-by-step method highlights the importance of correctly applying the stoichiometric coefficients when writing the KSP expression. You may be wondering, why is this useful? Solubility product has wide applications. It helps us predict whether a precipitate will form when two salt solutions are mixed, a fundamental idea in qualitative analysis. For instance, silver chloride precipitates earlier than silver chromate because its KSP is smaller. In industry, KSP is used in metallurgy for selective precipitation of metals, in pharmaceuticals to control solubility of drugs, and even in water treatment for removing impurities. So this concept is not just theoretical, it's deeply practical. So to wrap up, we've seen that solubility depends on the delicate balance between lattice energy and solvation energy. The solubility product constant, KSP, gives us a numerical way to connect equilibrium ion concentrations with solubility. By applying stoichiometry, we can calculate molar solubility from KSP values, and this knowledge helps us in both laboratory analysis and industrial applications. Always remember, the smaller the KSP, the less soluble the salt. I hope this session helped you appreciate how a simple constant like KSP governs such important processes around us. In our next class, we'll see how common ions influence solubility even further, a beautiful application of Le Chatelier's principle. See you then.